Hi there, folks. My name is Mr. Los. I want to talk to you about the ideal gas law today. The thing I'm working with right now goes along with a document that at least I made available on my distance learning page. And so you're going to want to find that. If you can print it, but if not, you could just have a digital version that maybe you could look along with and do some of the work on your own paper. Okay, so earlier in the year, we talked a little bit, at least in my class, about gases and some of the variables that are involved with gases that affect gases. Well, this is a mathematical equation that ties together all the variables that can affect a gas. I like to call it PIVNERT to kind of help remember, but officially it's called the ideal gas law. But if you say PIVNERT, that it kind of looks, you kind of pronounce it how it looks. So pretty straightforward for most of these things. P stands for pressure, V for volume, N stands for moles, which is kind of weird, but M is already taken by meter, I guess. I is something called the ideal gas constant. It's just a magic number that makes this work. It's the same for every problem. You never need to be told R. And T is the temperature. So as I mentioned, R is a constant, and that is its unit. It's liter atmosphere per Kelvin mole. The formatting looks a little bit weird. Don't worry about its unit that much. But yeah, something like that. Now, the thing about the ideal gas law is it requires very specific units. Pressure must be in atmospheres. Temperature must be in degrees Kelvin. Volume must be in liters. And of course, N has to be in moles. Now, if you don't know about Kelvin temperatures, it's a different temperature scale. 0 Kelvin is as cold as it can be. It's absolute zero. So the way you turn Celsius to Kelvin is you add 273 to the Celsius temperature. So really simple. And I'll show you some examples. But if you do happen to be given a temperature in Celsius, you just add 273 to turn it to Kelvin. Okay, so we're going to do just a little bit of algebra here. When we're looking at a problem, we want to check over, make sure we have the correct units that we need. If we need to convert any units, we'll convert them. If not, we'll just do some algebra and solve it. What I think I'm going to do here is pop off my little camera because I'm going to flip this down. I will work these on pen on the little Word document that I have open here. So the equation is PV equals nRT. And a sample of carbon dioxide gas is collected in a 2-liter container. There's my volume. The pressure is 3 atmospheres. The temperature of the gas is 208 Kelvin. How many moles of CO2 are present? So everything is in the correct unit. We got a Kelvin temperature. We got a liters. We got a pressure in atmospheres. So moles is N. I'm solving for N here. And I like to do the algebra first before I even start. So I want to get N by itself. One of the big rules of algebra is if you want to get something by itself, do the opposite of whatever being is done to it. So N is being multiplied by RT. So I'm going to divide both sides by RT. And so we see that PV over RT equals N. And so now all I need to do is plug some of these numbers into the equation and solve this bad boy. So on the top, my pressure is 3 atmospheres, straight from the problem. My volume is 2 liters. R, I do not need to be told R. I can just put in 0.0821 for R, and I'm going to write the unit just this time. It's a liter atmosphere per Kelvin mole. And then the temperature is already given to me in Kelvin, it's 298. Now, just to show you what happens here is this Kelvin is going to cancel with this, and something that's in the numerator of a denominator will cancel with something in the numerator. So it all cancels like that. It leaves me with a unit of moles. Not a huge deal, but I just want to show you why it has that unit. So basically, all I need to do is do this computation. If you have a graphing calculator, I recommend putting it all in your calculator at once, but do make sure you put parentheses around this bottom part just like I have it here. And so if you get that into your calculator correctly, you should get about 0.245, probably 2 significant figures here. So let's call it 0.25 moles. Limited to 2 sig figs, mainly because of that number right there. Okay, so let's just go ahead and take a look at another one. So hydrogen gas is being stored in a 1,500 milliliter container. The pressure is 2.74. It's 0.2 moles of oxygen. What is the temperature of the gas? So I do need to make a unit conversion here I need to convert milliliters to liters. And at least in my class, we've had some discussions about this. We're going to move the decimal over 3 spots or divide it by 1,000 or use the staircase, however you want to do it. But this is 1.5 liters. Two significant figures there. So I'm solving for temperature. So PV equals nRT. And again, the big rule of algebra, T is being multiplied by nR. So I'm going to divide both sides by nR. And so I get PV divided by nR equals T. So just a little bit of algebra there. Everything else here is in the right unit, so I'm going to plug in 2.74 atmospheres. And my volume, I'm going to put it in liters, 1.5. And then N is 0.2 moles. And R is, I don't need to be told R, it's 0.0821. So then I just need to do that computation. Again, if we put it all into a calculator at once, make sure we put the parentheses where I have them here before you multiply them out. You're going to get about 250.3. Now, by the way, the ideal gas law will always put out whatever units are being required. So since Kelvin temperatures are required here, it is going to give us a temperature in Kelvin. And by the way you're supposed to write Kelvin is just with a capital K, no degrees symbol or anything like that. Probably not a huge deal if you do. And by the way, I know I'm moving through these kind of fast, but of course, feel free to stop, pause, go back, relook at things if I'm going a bit fast for you. Okay, so example 3. Large weather balloon is being inflated with helium gas, 12 grams of helium gas. That's the unit we're going to have to convert. We need moles, not grams. The temperature is 30 Celsius, so another unit we're going to have to convert. What is the volume of the balloon in liters? So let's take care of those unit conversions before we do anything else. Let's do the one that's a little bit even easier, which is Celsius to Kelvin. So you just add 273, and that's always what's going to change Celsius to Kelvin. So Celsius is 303 Kelvin. And then the 12 grams of helium, N is moles. So 12 grams, 1 mole of helium has a mass of 4 grams. That's straight from the periodic table. So that's 3 moles of helium. So now that we have that taken care of, we can just do some algebra and plug stuff into the equation and solve them. So PV equals nRT. So in this case, we're solving for volume. Volume is being multiplied by P, so I divide both sides by P to solve it for P. Volume is nRT over P. Now I just need to plug the stuff in from the problem. 3 moles times R, which is 0.0821, times the temperature, which is 303 Kelvin, all over the pressure, which is 0.94 atmospheres. And so again, I just need to plug stuff into that equation to solve it. I'm going to get about 74.62, probably 2 sig figs, 75 liters. So a weather balloon is like a big old helium balloon that you launch way up into the atmosphere, and it can, make recordings and stuff like that to help you make predictions about the weather and stuff. That seems like a reasonable size for a weather balloon. Okay, so those are the 3 examples. If you feel good, feel free to jump into the practice, but I think I might try one more with you here. Let's take a look at I'm going to take a look at number 5 here. Give myself a little bit more room. Okay, so a 50 milliliter sealed flask, going to have to convert that. Going to have to convert that. Pressure looks good. What mass of nitrogen gas does the flask contain? Okay, so the ideal gas law doesn't have mass in it, but it does have moles. So our technique here is going to be to find the moles first. But before I do that, 50 milliliters. We're going to convert that to liters by dividing by 1,000. 0.0500 liters is what that would be. And then 25 Celsius, to make that conversion, we just add 273. That turns to Kelvin, so 298 Kelvin. So now I have my correct unit, and again, my strategy here is going to be to solve for moles first, because once I do have moles, we know that we can always turn moles into grams. So PV equals nRT. If I divide both sides by RT, that's going to get moles by itself. So PV divided by RT equals N. So my pressure is 3.75 atmospheres. My volume is 0.0500 liters. And then my denominator here, 0.0821 times my temperature in Kelvin, which is 298. That's an 8. All right, so just solve that out for moles, and that's going to be, we need to be careful about significant figures here because we have a small number, and some of us will want to drop significant figures here, but we want to keep at least 3, and we want to remember that those beginning zeros are not significant. So that'll throw you off quite a bit if you, for example, round that to 0.008. The other thing we have to remember about nitrogen, at least in my class, we talked about Brinkelhoff. I've heard of some people who said Hofbrinkel, which is obviously ridiculous, but Brinchlhof. And remember, what that's to help remind us is all of the 7 diatomic elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So the reason I'm bringing this up is nitrogen is one of these Brinkelhof elements, and when we're talking about the element nitrogen all by itself, we should think of its formula as N2, not N. So what that's going to affect is the molar mass. Regular nitrogen's molar mass is 14.01, but I want to multiply that by 2. So we should consider the molar mass of nitrogen gas to be 28.02. So 0.0766 moles. And then 1 mole of nitrogen is 28.02 grams. So just a straight up gram to mole conversion like we've done many times before. So 0.215 grams. Okay. That's it. Of course, feel free to contact me with any questions that you have. Don't forget your Brinkelhof elements. If someone told you to say Hofbrinkel, that's silly, and stop saying it. Say Brinkelhof instead from this point forward. Thank you very much for watching, and we'll see you next time.